In this video, we're going to set up mice tables and incorporate the information from the equilibrium row into the mass action expression for Kc. This will allow us to solve for x and ultimately determine equilibrium concentrations. Once the mass action expression is set up, there are three strategies to solve for x. First, we want to look for a perfect square. This means that there is a squared term in the numerator and a squared term in the denominator. Always check this first, because if it's there, then we can solve the problem without making assumptions or solving the quadratic equation. This is the focus of this video, solving problems that have perfect squares. If there is not a perfect square, the next approach is to assume the change in x can be ignored, which simplifies the math. If we do this, we have to go back and check the assumption. This is the topic in another video. If the assumption fails, then the third type of calculation is to solve the quadratic equation. This is also a topic in another video. I mention all of these here, though, because it's best to run through them in order until you land on the appropriate method for a given problem. Perfect square, assumption okay, quadratic equation. Once we solve for x, we need to go back and take a look at what does x mean. Is this what the problem was asking? Or are there additional calculations that we need to do? Finally, in case you're wondering, what's a mice table? We already learned how to set those up in another video, so you can check that out if you need to. So this problem is asking us to calculate the equilibrium concentrations of all substances in this reaction. The first thing we do is write down our reaction. N2 plus O2 goes to 2NO. We set up our mice table, initial, change, equilibrium. It's a mice table, so the units are molarity. And we're ready to fill in our initial concentrations. We have 0.100 molar for N2, 0.100 for O2, and nothing given for NO, and so we put a 0. Following the stoichiometry to apply that to our change in x, we have a minus x for N2, a minus x for O2, and a plus 2x for NO, because that balancing coefficient was a 2. We add the I and C rows together to get the E row. So we have 0.100 minus x, 0.100 minus x, and 2x. So we have our completed ice table. The next thing we do is write our mass action expression with variables. So we have Kc equals NO, or I should say the molarity of NO squared, divided by N2 times O2. The next thing we do is enter the information from the E row into our mass action expression and include the value of the equilibrium constant. So we have 0.497 equals NO, which is 2x, quantity squared. Be really careful with this type of a notation. A common mistake, I'm going to write it off to the side and then I'm going to erase it. The common mistake is to write 2x squared. That is not the same thing as quantity 2x squared. See the difference? So you want to be really careful about what part is being plugged in for the concentration and that whole quantity is squared. So now I'm going to erase that. So we have our 2x quantity squared in the numerator divided by N2, which is 0.100 minus x, times O2, which is 0.100 minus x. Notice that in the denominator, we have the same term multiplied by itself, so that becomes a squared term. So we end up with 0.497 equals 2x squared over 0.100 minus x quantity squared. That gives us our perfect square because we have a squared term in the numerator and a squared term in the denominator. So we simplify this by taking the square root of both sides. Don't forget to actually do the math and take the square root of the KC value. So we take the square root of the KC side and we take the square root of the other side. When we do that, we end up with square root of 0.497 equals quantity 2x divided by 0.100 minus x. So basically the squareds go away. So the square root of 0.497 is 0.705. So I have 0.705 equals 2x over 0.100 minus x. I'll cross multiply. So I have 0.705 times 0.100 minus x equals 2x. So now I need to simplify the left side. So I have 0.705 times 0.1. So I have 0.0705 minus 0.705x, be really careful, equals 2x. I add the 0.705x to each side, and I get 0.0705 equals 2.705x. Divide both sides by 2.705, and I've solved for x. Let's see. So we have 0.0705 divided by 2.705 gives me 0.0261. In terms of sig figs, it can get pretty messy to try to keep track of multiplication and subtraction and all this stuff. So when we're solving these more complicated problems like this, and we're solving for x, we'll keep the original number of sig figs. So our KC had 3 sig figs, so we'll go ahead and keep 3 sig figs when we solve for x. Now if we need to do a subtraction in the ICE table, then we'll follow the rules of decimal places. But this will just help us, I think, not get too bogged down with the significant figures. So we solve for x, but that isn't actually what the problem was asking us to solve. It was asking us to solve for the equilibrium concentrations. So now we'll need to do a couple more calculations to get to those final values. So you can see right here in our E row what math we have to do to get to each of those concentrations. So our N2 and our O2, so I'll just set it up like this, are calculated by taking 0.100 minus x, so that's 0.100 minus 0.0261. Keeping track of decimal places, our original value went out to 3 decimal places. We have 4 decimal places in our x, so we need to make sure that when we do this math, we're keeping 3 decimal places. 0.1 minus 0.0261 gives us 0.0739 or 0.074. The units are molarity because that's the way that we had set up the ICE table. For NO, we calculate the equilibrium concentration as 2x. The 2 is exact, so it's 2 times 0.0261 And that gives us 0.0522. Again, the units are molar. So our final result, N2, 0.074 molar, O2 is the same, and NO is 0.0522. So our next example will approach in the same way. We'll write down our equation, 2 HBr going to H2 plus Br2. Setting up our table, we have ICE, units of molarity, and we'll fill in the concentration information that we're given, 0.010 for HBr and 0 for H2 and Br2. The change for HBr is minus 2x because there's a balancing coefficient of a 2, and plus x for H2 plus x for Br2. The equilibrium rho is 0.010 minus 2x, x, and x. The next thing we do is we write our mass action expression with variables. So we have Kc equals H2 times Br2 divided by HBr squared. Now we'll plug in the information. We'll enter the information we have from the equilibrium row and for Kc. So we have Kc 2.4 times 10 to the negative 16 equals x times x, or x squared. I guess I'll start it like this. X times x divided by 0.010 minus 2x quantity squared. So we're just dropping in the values from the E row into our general expression for Kc. We recognize that this is a perfect square because we have x squared divided by the quantity in the denominator squared, 0.010 minus 2x squared. So that perfect square will allow us to take the square root of each side. So we have the square root here and the square root here. So 2.4 times 10 to the negative 16, taking the square root, keeping it at 2 sig figs, gives us 1.5 times 10 to the negative 8 equals x divided by 0.010 minus 2x. So we just get rid of those squared terms. Cross multiplying, we get 1.5 times 10 to the negative 8 times 0.010 minus 2x equals x. So we have 1.5 times 10 to the negative 8 times 0.010 gives us 1.5 times 10 to the negative 10 minus 3.0 times 10 to the minus 8 x equals x. So now we can add the 3.0 times 10 to the negative 8 to the other side. So we have 1.5 times 10 to the negative 10 equals x plus 3.0 times 10 to the negative 8x, and rounding to proper sig figs, basically giving us the 2 sig figs that we have from our Kc. Essentially, this just stays at x. The number that we get, so just so you don't think I'm making things up, is 1.000000003. And so we're not taking our values out that far, and so it is safe to just call that 1. So the solution is x equals 1.5 times 10 to the negative 10. What were we trying to solve for? We were trying to solve for the concentration of bromine, which is right here. So it turns out that that is equal to X. So the concentration of bromine is 1.5 times 10 to the negative 10 molar. So here we go, our last example. Hopefully you're starting to see the patterns and how we go about, how we apply the strategy, how the problem solving is essentially the same every time. We have some different numbers, we have some slightly different math, but the general strategy doesn't change. And you want to get to that point. So let's write down our last reaction. So we have CO plus H2O goes to CO2 plus H2. Set up our labels, ICE, units are molarity, and we enter our initial values. We have 0.133 molar for carbon monoxide, 0.133 for water, and zeros for the other two. The stoichiometry in this example is all 1-to-1. So we have a minus X, plus X, and plus X. Our equilibrium row then is 0.133 minus X, 0.133 minus X, X, and X. We write our Kc, our mass action expression, so we have Kc equals CO2 times H2 divided by CO times H2O. So we have our Kc set up, our mass action set up. Now we're going to enter what we have. So we have 1.56 equals X times X divided by 0.133 minus X times 0.133 minus X. We notice that we have a perfect square, which is X squared divided by 0.133 minus X, quantity squared. So we can take the square root of both sides. The square root of 1.56 is 1.25. So we have 1.25 equals X divided by 0.133 minus X. Cross multiply. 1.25 times 0.133 minus X equals X. Then we have 1.25 times 0.133 gives us 0.166. 0.166 minus 1.25x equals x. We'll add 1.25x to each side. That gives us 0.166 equals 2.25x. And then we can divide both sides by 2.25 to isolate x. And we end up with x equals 0.0738. So the question is asking us to solve for the equilibrium concentrations of everything. Our CO2 and our H2 are equal to X. So I'll start to write these over here. So we have CO2 equals 0.0738 molar. Our H2 is the same. We have to do some math for the CO and the H2O. We have 0.133 minus 0.0738. Keeping track of the decimal places, like we did in a previous example, we have 3 decimal places and we have 4 decimal places, so we need to round this to 3 decimal places. So we have 0.133 minus 0.0738 gives us 0.059. 0.059, that's our 3 decimal places. So our CO, 0.059 molar, and the same for our H2O.